Good morning, good afternoon, or good evening, I guess. Again, my name is Heather Paisley. I'm a postdoc with La Trobe University, an affiliate with CSIRO, and I came here to build the Mungbean model for APSIM NextGen, which I'd like to talk about for the next 10-15 minutes, the same as Neil did, and then we can talk about it. I have the model open for documentation and get into more detail. Before I get started, I wanted to acknowledge the traditional owners of this land on which we meet and acknowledge that we have much to learn from them when it comes to being stewards of the land for a sustainable future. I'd also like to thank the people who have helped me with this project and supported the work. So at CSIRO, La Trobe University, specifically Marissa Collins, the GRDC project at all, including RCN, Kylie, Millie, all of these people from Coffee who have given me so much guidance as to how mung beans grow, as they know it much better than me. And the APSIM initiative, specifically Dean and Neil, and then within CSIRO, Lindsay Bell, who is my other supervisor here. For those of you who have never seen a presentation from me, a small warning, I have a more different way of presenting data than Neil does. So I summarize everything as comic strips. So this is just an outline of what I'll be going through today, the process. So similar to what Neil was talking about, I started out with the plant modeling framework, specifically looking at the soybean model, which you see there on the left, fit data to it regarding related to 28 different experiments spread over 18 different locations with a variety of 8 different cultivars, different times of sowings, irrigation, water regimes, and fit the data to turn it into a Mungbean model and then validate it based on that data as well, which you see there on the right. More specifically, you can see the outline of the model here on the right of the screen, where the boxes are measured data from various experiments, and then the circles are values parameters that I deduced from that measured data. So on the right side, the temperature driving phenology, we have 10 different stages of phenology, and I'll get into how that was outlined in the next couple of slides. And then on the left side of that top figure, the partitioning or the accumulation of biomass and the partitioning of it into its different organs, and then the stresses that impact that accumulation and the senescence. Then in the bottom center, that's the nitrogen dynamics. So I was lucky enough to have data for nitrogen fixation as well as the partitioning of nitrogen throughout the plant, which also fed into the model. So during this, I'll go through the phenology, the Canopy Development, which followed a simple leaf approach. Senescence, I added an extra form of senescence to reflect what's happening in the field. And then the statistical results, sub-validation scenarios, sensibility analysis, and then ending with the limitations of the model. So starting out with the phenology, this is very much a repeat for what we just heard from Neil with the canola model. So thermal time was interpolated over 3-hour intervals. And for this model, I divided it into 3 different phases. The pre-emergence, the accumulation is shown there in the upper right corner, with thermal time based on that interpolation. Vegetative, which is emergence to the close or the end of canopy development, and then reproductive, which is the end of canopy development up to harvest, right? What you'll notice when you look at the pre-emergence is that delay in accumulation is to allow for a delayed emergence that people were noting happened, growers were noting happened when you planted mung beans earlier in the spring. So that puts that right into the model, that delay, and I'll show that a bit later. For vegetative, the optimal nitrogen or the optimal accumulation was around 28 degrees. And then reproductive, we found that as the temperature went up, it was an increased rate at which the plant was reaching its maturity at those higher temperatures. For Canopy Development, we had detailed data from specifically Kylie Grant's study on timing of sowing for Thomas' dissertation under Mike Robinson from years ago that took us to the nodal rate as well as the days to various stages. This is showcasing an additional study that we did using the jade cultivar, which is the most popular variety of mung bean in Australia, grown about 90% of the mung bean grown here, where the points are the real data, the lines are the simulated data. We took measurements of the node number there on the left and the branching rate on the right. This was pretty similar for most of the modern cultivars. Slightly different, we had a different data set for the older cultivars to feed into the phylocron. For senescence rate, as I mentioned before, I added in a new or a different way that the plant can senesce. So we had the age-driven senescence rate, which is typical for many of the other models in the PMF framework. And this is more of an accelerated senescence as closer you get to maturity based on the time of the thermal time alone. And then we have a water-driven senescence rate that would be initiated at the end of canopy development, where when the leaf FW, or the status of water in the leaf, reaches 0.15, so there's a slight amount of stress, we have a rate that if that exceeds the age-driven senescence rate, it's the dominant senescence rate that is occurring in the plant. And the way that we found or parameterized this senescence rate is we looked at some detailed data we had from Thomas's dissertation back in 1990, which had multiple different water regimes and looking at how mung bean responds to irrigation or stress. So on the bottom left there, we have the total water in the top 160 millimeters of profile, where the yellow is fully irrigated, the green is rain-fed, and the red is a terminally stressed treatment where rainout shelter was applied 45 days after sowing. And then on the right, you can see the senescence occurring. So with the green and slightly earlier senescence occurring, and then the red, a much more extreme occurrence happening there, showing the plant's response. Statistically looking at this is just the harvest data of the biomass on the left and the yield on the right, with predicted on the x-axis and observed on the y. We were able to get slopes close to 1 and predicting biomass within a ton and yield within 300 kg per hectare. The RSR and NSE for biomass would be denoted as a good fit, and the yield very good, or the 3 stars asterisks on the GitHub. And the p-bias showed that the model didn't tend to over or underpredict either yield or biomass. We were lucky enough to have a couple studies that looked at time of sowing. So this is an example from Kylie Grant's study in Gatton, which looked at 5 different times of sowing with 6 different cultivars. Again, this is jade, which is the most popular cultivar in Australia, and we were able to look at that early to late planting for biomass accumulation, grain weight, as well as a number of other variables. What we were able to achieve, especially with that pre-emergence thermal time accumulation, was the delayed accumulation of biomass at that earlier rates and still a quicker emergence at those later rates. But you'll see that with the biomass, we weren't quite able to get the harvest index exactly right for all of the different sowing times. This could be in some cases like the green, which is the January planting when there was more water, that was more rainfall during that season or that planting time. And the same with October planting. But also is that Mungbean is slightly indeterminate. So at the point at which the crop in the model is seen to have reached maturity, and in the field sometimes differs, there's a range of about 7 days of error in there that we couldn't quite nail down, just given different managing practices in the different trials. For water status, Mungbean is a rain-fed crop primarily, but for growers who are looking to increase their yield, there's interest in targeted irrigation. And various studies have found that irrigation during the pod filling has increased yield to close to being fully irrigated. So we wanted to make sure that the model was able to capture this impact as well. This is an example of one of the simulations we did. We also did targeted irrigation during the vegetative and the grain filling to make sure that we were really capturing that was really just happening during that pod filling. And we were right. And we see that with the yellow, that's our rain-fed. The blue is the targeted irrigation, and the black is our fully irrigated. So we got that for biomass and for grain weight. For our sensibility analysis, we did a factorial by sowing date and initial water. So the green there is the initial the water, the colors of the different water statuses. So green being low or 20% of a full profile of plant available water. Blue is medium or 60%, and high is 100%. And this is building off of soil profiles that we used in the model building data set. The different line types are the different times of sowing. So solid is early, planted in October. Mid is planted in December, which would be optimal in a lot of sites in Southeast Queensland, and late is February. On the left, that's our Gatton site where we had most of our detailed data coming from. And what we expected, because Gatton has a short ideal season and temperate climate and a vertisol, was that water would play a factor, but time of sowing would be a larger factor, driving the probability of higher yield. And we saw that where you can see that, especially if you planted late, you don't get quite the same chances of a higher yield. In that center graph there, it's a long season arid vertisol. This is down from Narrabri. And because it's a long season for optimal, we didn't expect the timing of sowing to have a great impact on the yield, but water would be a larger driver because it is an arid environment. On the right there, that's our site out of Catherine in Northern Territory. And so this would be that we would expect the optimal timing of sowing to be much later than what we were seeing in the New South Wales or Queensland site. And we saw that, yes, when you have low water and you plant way too early, you don't really have any yield. The plant might not emerge. And that early date is never going to yield much versus when you get later and finally to the late sowing rate, you're getting that optimal planting or sowing window. And that water is not going to be quite as crucial as the sowing date did. So our sensibility proved or showed what we expected it to do. The limitations of the study or of the model hopefully will be rectified in the next year or so with accumulation of more data. So the database was relying solely on field-based data, and we were only sourcing that from Australia. There are studies out of Asia, but they tend to be largely glasshouse. I've recently come across a potential source of field-based data from Sri Lanka and India, so hopefully that can be incorporated in the future. And there is some data out of Victoria which hopefully can be incorporated in the future as well to expand the model beyond what right now it mainly simulates, which is Queensland. Still, we did have data from 4 different states in Australia, and it did perform well across all those environments. When we looked at the studies that have come out of Asia, we found that the theory that was behind the model parameters that we calibrated here for this model were consistent with the findings out of those studies there. Also, it would be great to get more detailed phenological data for the more minor Australian cultivars. Jade is very similar to the most popular cultivars planted in Australia, and the performance was good across all of the cultivars that we calibrated to. But it would be nice for especially the ones that have shown to be a bit different beyond to get node appearance rate and a detailed phylochron. Again, with the Asian cultivars, we really don't have much information right now. As Mungbean is largely grown in Asia, that would be great to get more of. So in summary, where are we now? Overall, the new model performs quite well, especially when it comes to yield, biomass, but also nitrogen dynamics, water stress, and time of sowing. What are we missing? We're missing data from outside of Southeast Queensland, specifically Asia, New South Wales, and Victoria. And we could use more phenological data from more cultivars, specifically Asian and minor Australian cultivars. But we were still able to use the model to target all of our aims, which is why we build the model. So our various sensibility tests showed that we were able to target when and where to sow, when and how much to irrigate to see that yield boost, and that can be used for risk level management on both of those fronts.